Hello everyone once again. Today we are continuing with the grade 12 physical sciences paper 2 from November 2022. So we've already done questions 1 through 4 in previous videos. In this video we're going to take a look at question 5. Okay, so the previous 3 questions were all organic chemistry, and it seems now with question 5, we're switching gears to reaction kinetics. So let's get straight into the question. 3 experiments, A, B, and C, are carried out to investigate some of the factors that affect the rate of decomposition of hydrogen peroxide. Okay, so they give us an equation here. We have hydrogen peroxide decomposing into water and oxygen. And there's 3 different experiments. So we have experiment A at 25, experiment B at 25 as well, but with the catalyst. We have experiment C at 35 without catalyst. Okay. So just some general information in the preamble of the question, no problem. Okay, so the balanced equation is given, identical samples of hydrogen peroxide were used, the conditions of each are given. Okay, so starting off with 5.1. In which experiment, A or B, is the reaction rate higher? Use collision theory to explain your answer. Okay, so A and B are both at the same temperature, but one is with a catalyst and one is without a catalyst. So we should already know that catalysts act to improve our reaction, or at least increase the rate of reaction, whilst inhibitors act to slow down the reaction. And of course, a reaction that has a catalyst would be faster than a reaction without it, as long as they're at the same temperature and it's the same reaction. So here the answer is of course B. Okay, but this question is out of 4 marks, and they want us to use collision theory to explain why a catalyst increases the rate of reaction. So there's a couple of points, key points to notice here. The first is understanding how a catalyst works. So if we draw an energy diagram, okay, and we have energy, I'll just say delta E, and as the reaction proceeds, so reaction proceeds with the x-axis, okay, what we have is we'd have the starting energy of our reactants. I'll just say react. And then we have some energy hump. And then depending on the reaction, if it's a exothermic reaction, then energy is given off and our products would be down here. If it's endothermic and not exothermic, then our final state would be somewhere here. So we're just going to go ahead and assume that our reaction is exothermic. It doesn't really matter. And that our final energy level of our products is lower than our starting. So this difference here, this to here, okay, so this here is our activation energy. And then the difference here, that is the enthalpy of the reaction. Okay, so this is the enthalpy of the reaction, the actual energy, the net energy needed for the reaction, the net energy change. So that's more thermodynamics. So we're not too worried about the enthalpy in this question. We're more worried about the activation energy. So what a catalyst does is it interacts with the reactants to offer an alternative pathway in order to lower the activation energy. So with the catalyst, we would have something like this, okay? What's important is that the start and the end are the same. Just because it provides an alternative pathway, our EA is lowered. It's much smaller with the catalyst, okay? All right, so now that we have that in mind, what can we say, okay? So there's a couple of points, you can phrase them differently, but the key ideas are that the catalyst provides an alternate route of lower activation energy. More molecules have enough sufficient kinetic energy. More effective collisions happen per unit time because of this. So you can phrase it differently, but the idea is because the activation energy is lower, then each molecule on average has more energy, more kinetic energy, and they collide with each other more often, and therefore the reaction happens quicker. And for that, you'll get your full 4 marks. Okay. Let's move on to question 5.2. The Maxwell-Boltzmann distribution curve X and Y for two of the above experiments are shown below. Okay. Identify the curve X or Y that represents experiment C. Okay. So experiment C. So the first thing to note is that the area under these graphs would be the same. Okay. The difference is where the average kinetic energy lies. Okay. That's the difference. And what you gotta notice is that the average kinetic energy is where the hump is the highest. Okay, so let me just make this a bit tidy. Okay, so the average kinetic energy, okay, is where the tallest part of the hump is. Okay, and okay, if I'll just write 5.2 here. And the thing is, kinetic energy is related to temperature, yeah? So the reaction at the higher temperature would have the higher kinetic energy, okay? So it makes sense that C would have a higher average kinetic energy and therefore is correlated to Y. Okay, so therefore Y is C. Okay, all right, let's move on to 5.3. The volume of oxygen gas produced in experiment B during the first 3.6 seconds is collected in a syringe as shown below. Okay, so let's just make a note of that. So that's oxygen, 3.6 seconds. Okay, and the volume collected here, I would say that's halfway between 480 and 640, which would be 160. So 80, 480 plus 80 gives us 540. So this is 540 centimeters cubed. Okay, write down the volume of O2 collected in the syringe. Okay, well, you've just done that. All right, wait, but let's do it properly. I'm not sure if I've done it properly. Okay, so 5.3.1. So the syringe is between 640 minus 480. Okay, let's do some really basic maths. Okay, and then we need to divide this by 2 because it's halfway, as we can see there. So half of 160 is 80, and then add this back to 480. Gives us 560. Yeah, so I thought I had added that wrong. So this is actually 560, not 540. Okay. So therefore, our volume is 560. Okay. Calculate the mass of water that was produced during the first 3.6 seconds. Take the molar gas volume to be 24 cubic centimeters per mole at 25 C. Okay, calculate the mass of water. All right, so so they've only given us oxygen, yeah? Okay, so we have 2H2O2 going to O2 plus H2O. Or let me write this in red because this is what we're after. Okay. Okay. So we want to know the mass of water. What we have though is we have the volume of oxygen. And then in the question they tell us assume the molar gas volume, i.e. 1 mole of gas is equivalent to 24,000 cubic centimeters. So with this, we can calculate our moles of oxygen. So our moles of oxygen is equal to 560 over 24,000. And this gives us, let me just get my calculator. Give me a second. So this gives us, and just punch that in, 0.023, just add another 3, but it's 3 recurring moles of O2 gas. Okay. All right. And what we can see here is that the molar ratio, there's a 1 here, don't have to write it, but it's there. The molar ratio of O2 to H2O is 1:2. So for every mole of O2 produced, double the amount of H2 is produced, H2O. So with this in mind, we can calculate our moles of H2O. Okay, this is equal to 2 times the moles of O2, which equals 2 times 0.0233 mole, which gives us 0.0466 mole. And double check with the calculator, but I mean, I just did that in my head. That should be correct. Let's double check with the calculator. 0.466. Yes, correct. Okay. So now we know the moles of H2O, but they didn't ask us for the moles. They want us to get the mass. So we need to remember that moles equals mass times molecular weight. So mass equals moles, or we can just write it as N over MR. Okay, so now we already have N. We just need to figure out what MR is. So H2O, we can just take O to be 16 and this to be 2. So the MR is about 18. Okay, so we can just take it that way. So with that in mind, oh, whoops. Okay, so with that in mind, we basically have 0.0466 over 18, and that gives us a mass of 0.00259 grams. Wow, that's really small. You could rewrite this if you wanted to as 2.59 milligrams after 3.6 seconds. All right. Have I done this correctly? Oh no, I haven't done this correctly. I got the formula wrong. It should be... Yeah, no, I got the formula wrong. I got this beginning formula wrong. Yeah. So it should be mass equals moles times molecular weight, which then equals the 0.0466 times the 18. And then this gives us our true answer, which is 0.83 grams. So I had done it wrong. That's why the answer was really small. That's why I had to double check, because the answer seemed really small. So we just have to remember that our equation that, well, it's given to us at the end of the paper as well. I just don't have the full paper. But at the end of the paper, the equation is given where N equals M over MR, right? So this is moles equals mass over molecular weight. Molecular weight. Okay. And if you want to make mass the subject, so just taking it back, it's M, then it becomes MR times N, which is what we have here. So I had the equation backwards. But okay, we get our answer. Nice. Let's move on to the next one. Question 5.4. Okay, the graph below, not drawn to scale, is obtained for the mass of oxygen gas produced over a period of time in experiment A. Okay. Use the information in the graph to answer the following questions. Okay. Write down the rate of production of oxygen gas in the interval 30 to 36. So here. So here we have mass of oxygen, okay, and time. So what we can see is that for this region of the graph, this line is not changing. It's staying straight, yeah? So the mass of oxygen is not changing. It stays 0.9 for this whole time. So for this region, it's a bit of a trick question. The production of oxygen is just 0, okay? Because we can see that the line is staying flat, not changing. Will the rate of the reaction in the interval 3 to 9 be greater, smaller, or equal to the rate of the reaction in the interval 9 to 20? So 3 to 9 here compared to 9 to 20 here. Okay, so what we can see is that the time difference between 3 to 9 was 6 seconds. So for 3 to 9, it's 6 seconds. And the difference in mass, so at 3 seconds we have 0.4 and at 9 seconds we have 0.6. So the mass is 0.2 grams. Okay. For 9 to 20, the time is 11 seconds. And the change in mass is from 0.6 again to 0.8, so it's 0.2. So what we can see already is that for 3 to 9, it's the same change, okay, but in less time, 6 seconds versus 11. So the rate here is faster than the rate here, okay? So yeah, so here the answer would be greater than, okay, greater. All right, last question. The average rate of decomposition of hydrogen peroxide is that. Calculate the value of time t on the graph. So the average rate, okay, they want us to do some math. So the average rate is 2.1 times 10 to the minus 3 moles per second. Okay. So what we have here is that for this time, we have a mass of 0.1 grams. So, okay, 0.1 grams. So from 20 to t, we have 0.1 grams. Okay. So what we need to do is convert this into moles in order to apply our rate. For now, we can't apply our rate because it's not in mass, it's in moles. So let's do that quickly first. So let's remember our equation, N equals M over MR. And the MR of hydrogen peroxide is basically, this is 16 times 2, which is 32. That's 2, so that makes us 34. Okay. So here we have 0.1 over 34, which equals 0.00294 moles. Okay. Now let's multiply our moles by our rate in order to just be left with seconds, which is the time taken, right? So what we need to do here to get time equals rate times moles. And this is 0.00294 times 2.1 times 10 to the minus 3. And what do we get here? Okay, we get 0.00000617647. Okay, so what you got to realize is I've done it the long way because we have per second. I've essentially got the inverse, so you can just do that. More correctly, maybe what we were supposed to do was divide our moles. So divide that by this, by our rate. I've done it the longer way, but it's fine. So just take the inverse and then you get some answer. And my answer is really weird. What have I done wrong? I feel like I have done something horribly wrong. My answer is too big. So let's backtrack. Okay, let's backtrack. My answer is too big. Okay. So the first thing is that I see where I went wrong. Okay, so I went wrong because here they give us the decomposition of hydrogen peroxide, but the graph is in terms of oxygen. That's what I got wrong. Okay, so what I've done, what has happened here is I've got my wires crossed, and it's a 5-mark question. So it's really easy to get confused on these questions, especially the long ones that involve a lot of calculations. So yeah, you have to be careful. Okay, so let's think of this. So might as well just rewrite the equation. So we have H2O2 forming 2H2O and oxygen. And the rate of decomposition of this is given here. and that we want to figure out time t. Okay, so we know that for every mole of H2 decomposed, we have half a mole of O2. So the first thing is the mass of O2 between 20 and T is 0.1. So let's calculate that in moles. Okay, so we're going to do the same thing. 20 to T, 0.1 grams, converting to moles, N equals 0.1 over 32, because O2 is just 16 times 2, which is 32. Okay, and this gives us, we can just round it off, 0.028. But don't round off just yet. Just try and keep at least 3 significant figures. We'll round off at the end. Okay. And then what we got to realize is that because of the ratio here, so for every 2 moles of H2O, it's 1 moles of O2. So if we were to divide both sides by 2, we'd have half here. Okay. So the rate of O2 production is half the rate of H2O decomposition. So we need to say half times 2.1 times 10 to the minus 3, which is just 1.05 times 10 to the minus 3. Okay. So now we have the rate. Okay, now we have the correct numbers. So, okay, I won't do the long, I'll do the short way. So all we gotta do is basically what we can say is a rate is given in moles per second. Okay, so rate equals moles per second. So let's substitute into this equation. So we have our rate 1.05 times 10 to the minus 3, and then we have our moles. So our moles are 0.0281. Yes, and then our time is what we don't know. Okay, we don't know our change in time. So calculating for this, delta t would be 0.0281 divided by 1.05 times 10 to the minus 3. And this gives us 26.76 seconds, I guess. So that's what t would be. Okay. So, yeah. So we know that at this point, okay, the way I've done it is different. Yeah, the way I've done it is different. Okay, no. So this is if you were going to calculate, I made a mistake in my calculations here. This is supposed to be 0.003125. That's all correct. So let's just change this. Then we're going to get a small value for t here. Okay. (0.003125) divided by 1.05, 10 to the minus 3. This gives us 2.976. So this is the time for this interval. And then basically, what we have to do is add it to 20. So to get the value of t, it would be the previous no, we need to subtract it from 30 because the rate is decreasing. So to get the previous one, what we would say is 30 minus this, and then yeah, we get something close to the answer. Okay. All right. That's better. Okay, there's a couple of ways of doing this question. This is a really tricky question. You really need to understand that the rate is changing. That's the tricky part. So this is just some average rate. So really the way I've done it is probably not the best way. It might be more accurate to like take the total mass. So to just say at this point, the total mass is 0.8, and at this point, the total mass is 0.9. And then calculate that way. But the way I did it is I just took the difference between these two. That's why I worked with 0.1, and then I calculated the average time, that should be this, and then subtracted from the next value, which is 30, which is actually not the most accurate way to do this, because the actual answer should be 26 point something. That is an acceptable answer. So 26.7, 26.6. We got 27 because we didn't do it the most accurate way. You'd still get part marks if you did it this way, the way I've done it. But it's not the proper way of doing it. But it does just highlight that there's quite a couple of different approaches to this question. But we got an answer that's pretty close. This is only an average rate, and that's why it's better to use the numbers 0.8 instead of 0.1, which is what I used. But yeah, with that, that concludes question 5.